surface tension. We say surface tension is force per unit length. It is the characteristics of a liquid that makes it, that is the surface, act like a stretched elastic material. To represent surface tension, this is like T that is bent with force over M, that is meter per Newton per meter. Now, I said that all these things we are saying, to understand surface tension, it is simply the force, the inward force that the molecules of a liquid experience. Just like we normally say that surface tension depends on temperature and nature of the material. So it depends on temperature, and nature of material. So what this means is that if there is more heat on this, the higher the temperature, the higher the surface tension, because if there is heat, the molecules down here will tend to gain kinetic energy. It will move up. The one up will tend to move down. It will gain kinetic energy if there is heat applied and move up. The one up will come down. So we say that it is the inward force. The inward force on the molecules of a liquid that tends to pull it down / inward when kinetic energy is acquired, or as kinetic energy is acquired. So you need to know this. And this surface tension that you see like this now, this surface tension that you see acting inward is more like I have this liquid, the ones up are being drawn downwards. After this, the second force I want us to look at is what we call adhesion. So notice that this adhesion, we say that it is the force between a liquid and the containing vessel. So it means adhesion force means the attraction force or affinity a liquid has for the containing vessel, or you say for the surface in contact with. So if, for example, I pour water in a glass, that water naturally has adhesive force. It has adhesive force more than its cohesion force or its cohesive force. We'll talk about that one next. So this adhesive force that it has more means that it has affinity, it has that tendency to be attracted towards the containing vessel, towards the glass. So some of it we have to leave and wet the glass. So because of that, we say that water has more adhesive force. So if I know this, we normally say whenever this is the result of, if I pour water, if I drop, like if I have a drop of water land on a flat surface now, a drop of water land on a flat surface. Let's say this is the flat surface. This water now that you see will tend to move in such a way that it is almost going down, like it goes in this way. Should I say it is flowing to the point that it is having to go directly to touch the glass, or sorry, to relax on this surface. Sorry, we are not talking glass here. To relax on this surface. So if I want to check the angle of contact here, I can see that this is a tangent. We'll come to that. This is a tangent, that is a line that is touching where this water, that is the spaces made by the water and the container. Now from the inside, if I measure it, you see that what I have here from this line, if I check this line, if I have this to be the line and this angle here is less than 90. The angle is less than 90. So whenever you have adhesive force, whenever you have an adhesive force acting more on a particular liquid, the angle will be less than 90, and this is the way it will look when dropped on a surface. So if I know that, we now say that if we carry this liquid that experiences more adhesive force and put in a cylindrical jar, that by the time you pour it, that this particular liquid that experiences this will look like this. It will have a meniscus. This thing is what we call upper meniscus, and this meniscus that you see here, we say that this meniscus is a concave meniscus. So once you have adhesive force to be more, the attraction to the containing vessel to be more, you have a concave meniscus. That is, the upper part of it will look like a concave. This top surface is called meniscus when you have liquids that form shape. So if you have this, now if you check, let's say I draw that tangent, I'll still tell you what this tangent I'm drawing. Let's say tangent is simply a line that touches an arc, or touches a circle, touches anything at a particular point. So if I draw a tangent here, now this tangent now that I've drawn, this is the point where this particular liquid touches this glass here. Now this tangent that I've drawn, this is the glass itself, vertical. Now this is the tangent. There's an angle here. Notice that if I bring this angle out now, this angle is also less than 90. This is theta. So we say that even inside a capillary tube, the angle it will give us will also be less than 90 degrees. So it forms a concave meniscus. How do you know concave? Whenever you have, that time with treated lens, whenever you have something like this, it's concave. So see this part, and it produces diverging lens. If you still remember, another way to treat this concave is more like saying, if you are going into a cave, you go into a cave, so it will have something like opening to receive you, cave. If you remember when I treated this class lens, so that is all about. So concave, that is why you come and see this thing now up here, concave, and because it's on the top, concave meniscus. Now let's move to the next type of force. The next one is what we call cohesive force. From coherent, you know that when you say somebody say coherent, that person is saying put into one, understand, make all the aspects to be together. So from there you get cohesion. Whenever something is talking about cohesion, it's talking about being the same. But we normally say that cohesive force is the force a liquid has for itself, or you say it is the attraction force, or you say attraction of liquid to liquid. So you say it is the attraction force of liquid to liquid. So it is the force that brings liquids together. So normally the other one, The other one is the force that allows, that is adhesion force, is the force that allows each liquid pull out, is going out. But cohesion force is the force that tends to pull each liquids together. So if I drop a liquid now on a surface, let's say this is the surface, the minute this liquid land on this surface, instead of it trying to spread out, it is the one that puts it together. So in simple terms, I want you to know that adhesion force, you can relate adhesion force with liquid force that makes liquid spread out, force that makes liquid to spread out and causing it to be attracted to the surface of contact. Why? If you have more force of cohesion, that means that will make the liquid to be together. So the force that makes a liquid to be together, or you say it is the force of liquid composure. So whenever you hear cohesion, I want you to remember it with composure, liquid composure, liquid composure. So is this one I'm talking about. So if you want to check it now, if you draw the same tangent we drew in the other side, notice that tangent here, if you check it, this liquid is composed, it is together, the force that holds it together. So if I draw a tangent now, I will not draw it like this, because if I draw it like this, I've missed this side. So the tangent will simply be this way. So as I've drawn this tangent now, and now this is the container, that is, this is the surface in contact with. Now notice that if you check it, you are having something like this. So measured from inside the liquid, if I measure this angle from inside the liquid, see that this angle theta is greater. So angle is greater, angle greater than 90 degrees. An example of liquid that is like this is mercury. So a mercury, when you put it, when you drop it on a surface, this is how you notice it, because the cohesion force, the cohesive force is more than the adhesive force. So for that reason, it will give you an angle greater than 90. And if you choose to pour it inside a capillary tube or inside a cylinder, you will notice that when it enter here, it will come and round up on this. It will give you a convex. So how I normally explain this convex is, if you have something like this, and it gives you converging lengths, if you remember. So I normally take the vex there. When you vex or when you get annoyed, your face tends to swell up. Is it not true? So vex. So from vex, you know that it is the one that has to do with swelling up. So coming out like this, coming out like this. So just that is, this is for lens. If it's lens, we say it is the one that tends to be bigger at the middle and then thinner at the edges. So if I know this is from vex, I get it. So if for you to remember, it's an input convex. So if you know this, when it has to do with liquid inside capillary tube, if I choose to now come and want to draw tangent here, the tangent I will draw is just on this part, the part that touches it. The mistake people make is that they will come and have this thing now, as this thing is here, they come and draw tangent like this, draw tangent like this. You will forget where you are supposed to look at if you draw this thing like this. So it's not like this. Just draw the tangent any of this side, just from here. Now I can choose to as I have this thing like this, can choose to also draw it from this end, but let it not pass that glass. Now notice this is the glass, from the part where that's contact, the point of contact, then to the angle you've made. Now from this point of contact to the glass wall, and notice if you check the angle here, this is like this way, this is the theta, this is the theta. So if you check the angle you made, you see that it is definitely greater than 90 degrees. It is clearly greater than 90 degrees. So we say that once it has cohesive force more, it will always have an angle giving you that is obtuse. So we say that it is obtuse angle. Why? If the adhesion force is more, it will be acute angle. Example of this is water. Water adhesive force is greater than cohesive force. Why? Example of this is mercury. Cohesive force is greater than adhesive force. So if you want to represent this well, if I have this to be a liquid, and we want to do this well, let's say we have water here. So the one that tends to draw it to the middle is the cohesive force. The one that tends to draw it to this surface, that is to this place, to this container, is the adhesive force. So you need to know that. So let's move to the next thing, which is properties of liquid. So I've treated forces acting on a liquid, or you say in a liquid. I don't even know how to put it because both are correct. So properties of liquid. The first property is what we call surface tension, which we've treated. Now, yes, the surface of a liquid will always have tension due to the inward forces. Even the cohesive forces will always act on it, and the adhesive forces will also act on it. So it's now up to the one that is greater. So the first, surface tension, I've treated this one. Cohesion or cohesive force, adhesive force. Now the fourth one I want to treat is angle of contact. So all those angles I was showing you, those things are angles of contact. So we say that angle of contact is the angle between the tangents, that is where it is touching, tangent to the liquid surface, at the point of contact and so see the main thing here. So this is, see, the angle between the tangent to the liquid surface at the point of contact, and the surface in contact with, measured, very important detail, measured from inside of the liquid. So you can clearly see that what brings about angle of contact is the adhesive force, the cohesive force, and yes, surface tension, because surface tension is like a pressure but acting in one dimension, force over L. Maybe it's in two dimensions, it will be over area. So if you know this is the definition. So it simply means that when I have any particular liquid that, let's say for example, this is a liquid that is giving me convex meniscus, that the surface angle of contact is simply come to this is the point of contact. This point of contact, this is the glass down. The up one is not my business because this is where the liquid stops and it's showing me this. Whenever you pour liquid inside a capillary tube or inside a cylinder, especially capillary tube, it will always show you it's going upwards this way or pulling downwards. That is convex or concave. So if it is in this form, you can now clearly see that what I have here is the point of contact. This is the glass. And if I choose to draw a tangent now on this, tangent is simply where it's touching this thing. So remember the definition. So angle between the tangent to the liquid surface, the tangent, this is the tangent to the liquid surface, this is the liquid surface. At the point of contact, so you see, at the point of contact, that is where it touches the glass. This is the glass now going down. Now, measured from inside the liquid. So you can see that this is above 90 degrees. So obtuse for a convex meniscus. While if it gives me a concave meniscus, let's do the center point of contact. Tangent to liquid surface, this is the tangent. I can draw it both ways. At the point of contact, measured from inside the liquid. So from inside the liquid, you can see that this angle here is less than 90. So acute for concave meniscus. Now the next one, the next property, the fifth one, is what we call capillarity. So we always say that this capillarity has to do with liquids rise or fall in a capillary tube is known as capillarity. So it's now up to you to go and find out capillary. It's not up to you to go and find out what, sometimes you see it as one, no problem, it's capillarity. So we say that tubes with fine balls are known as capillary tubes. So we say that a capillary tube will either rise or decrease more if you increase, if you decrease the diameter, that is, if it is this way, and it is giving you, let me do it this way. So let's say I have this thing like this, and I have this way. Now, if I decrease the diameter, it will tend to increase. So we say that is, and remember, it will tend to decrease, when it is water. Yes, let me check that shit out. Okay, yes, I'm correct. So it will tend to increase. So once you for capillary tube, so what capillary tube tells you is just rise and increase. So all those other properties determine it. If it is in a concave meniscus, the minute you decrease the diameter, decrease in diameter will lead to rise in capillarity. While if this was like this and you come and decrease the diameter, that is, make the capillary tube to decrease, it will fall. So in a convex meniscus, or the one that gives you a convex meniscus, for example, mercury, This one is for example water. So decrease in diameter. So I've told you when you verse, your face swell up. When you're entering cave, you have to push inside to enter. So decrease in diameter will lead to fall in capillarity. Thank you. Subscribe to my channel.